Now, let us now start with example 1. So with this, we'll have script 1. So here, the purpose of this script is to extract earth pressures on retaining walls, and this will be actioned on a static 2D model. So this is basically the model. The idea here, like you must have read now, is not to show you how to run PLAXIS, but how actually to implement the Python script that will be distributed with this example, and this is the same for all other examples that will follow, so that you know how to execute the script and then verify it if you like, and then you keep it for similar projects of your own. So let us just remove this for now. We don't want to save it. So we will open PLAXIS 2D. So this is PLAXIS 2D. I open it, and we will see several stuff here. I will explain the model itself. So this is a model. So basically we have main soil layer, and we have a fill here that will be basically used to fill in the space here. Forget about these boundary conditions for now. These are for the dynamic analysis, which I will explain in the next example. So we have here for the dimensions, you can see here the dimensions. The excavation itself is 5 meters, and the retaining wall is embedded 2 meters into the foundation soil, and this dimension here is 4 meters, and the right dimension is 1.5 meters. So let us just have a quick look at the soil. So we have the soil. This layer is sand. Again, I'm just giving quick background. So this sand, I use the hardening soil model and drained, and this is the saturated and unsaturated unit weight for the mechanical. So I have E50 about 60 megapascal, and this is the odometer, E-odometer, and the E-unload reload about 3 times this, so to about 180 megapascal, and the stiffness is increasing with a power rate of 0.5. You need to refer to the manual if you have any issue with this. The reference pressure, which is the effective lateral stress at which we have this E50, which keeps changing or evolving, if you like, as the material experience stress and the strain. And this is C dash reference is 0.1 here, so it's sandy soil, so it's nothing. And they will have friction angle of 38 degrees, and the psi is 0, which is the peak friction, the dilatancy angle here. What else that would matter here? The interface. So I have an interface of 0.8, because you see here there is interface here, and the strength of the interface in relation to the main soil is 0.7. The initial, so basically I made this manual, gain of 0.5, and the OCR, the over-consolidation ratio, is 1. So that this is the first material. The second material, I made it just like an instance of the other one, because the purpose here is just to show you how to use a script. So this is a problem. So we went to mesh, and when we went to this mesh, we generated the mesh, but we also generated, which is the crux of this session, we generated a few points behind the retaining wall. These points will be stress points. I'll show them now. So select points for curves, as you can see here. You come here. Again, I suppose that you are familiar with this. So yeah, this is Yep, so these are the few stress points that I have chosen. So let me just spend a few minutes on that here. So you can see this is the interface that I have activated, and we have another interface here which comes back to if I go to structures. So these are the two interfaces. So back to the mesh. So I have here the option to choose select points. If I press escape, so the stress points will come back. I'm interested in the stress point, so I can just deactivate the nodes, or actually hide the nodes. This is a correct word. So I'm hiding the nodes now, so that you see the chosen stress point. Now, to choose this stress points, it's obviously an arbitrary process. So for me, I just chose a few points here. But if you want to make this streamlined in a consistent way, so one approach is to say, okay, if I go back to this, I'll show you something interesting here, and a new script, but this time it's not going to be Python script, but it will be VBA for Excel script that you can also use it. So here I have, if you see the coordinate of this point, so y is 5, and it goes all the way down to -2. So all in all, I have like 7 meters here of a wall where I can subdivide basically and choose the points. And if you see the x coordinate here, so the x coordinate here is 11. So one way to do this is to come here. I'll show you how I can delete this, and then I can load it back. So I'm deleting now all these stress points as if I'm doing this from scratch. So, and well, I'm just deleting this manually for now. So, and I will show you. Let me open Excel. So here is an Excel. If I press Alt F11, so I have a code here that I have generated. This is a code. So this code basically, it enables me, if I would like to generate nodes, I would input the X and Y coordinates needed. So these are just arbitrary ones here. I haven't done anything special about it. And if I'm interested in generating stress points, all I need to do is to enter the X and Y. And when I press this, so let us remove that here. Let us remove this one here. So when I press this one here, it generates the command that PLAXIS Output can accept and generate these points. Okay, so let us assume that we're going to do this. So I have a point here, say y is 5 meters and x is 11. So I can start here with y is 5 and x is 11. Okay, well, I don't have to do it exactly at 11. I can take a few centimeters right to it. Obviously, there is another option, which is you query the interface itself. So I would say here, say 11.05. X is not going to change, so assume that I will have this. I'm interested in the stress points. I'm not interested in the nodes, because if you are querying for stress, because the pressure here is basically lateral stress, which is sigma dash xx. So I'm not actually interested in this in the nodes, but that's fine for now. I will just focus on the stress points. And why I'm starting from 5, if I need to generate this every, say, half a meter or 1 meter, it depends. So I would just basically take here 4.5, and I will continue until I reach the value that I'm interested in. So this value here, if you remember, is -2. So I can continue with this. And I have -2. I don't need this. I'm interested in the, but -2 actually would bring me exactly at this point. So we can make this as, say, -1.8 for the sake of the, okay. If you delete this, and then you say, now generate syntax. So all the syntax is doing here is to generate within this column, actually the command for PLAXIS You will see in a minute how I use it. So generate, so it says I have generated. So this would be the command that PLAXIS needs. So you have the option here to either enter this one by one, which is not very efficient. If you have the VIP option in PLAXIS, copy this, and you go to here and go to expert, run commands, paste all of them, and they say run everything. When you say run everything, so basically all these points that are well spaced here with a half a meter in between, you generated all these stress points that you can see here. Okay, and this what we have actually in here. If I go here, so these are the stress points that I'm interested in. Okay, so I will not save the model here because I have already my few points. I don't want to spend the time running the PLAXIS itself because this is not the nature of the course. So I will remove this and I will go back to that, and I will just open my example again. So don't save. I have already, like I said, if you go to mesh, and I have already a few points. These points are not spaced every half a meter. It's just something arbitrary I have chosen here, and I am happy with this. So as we speak now, PLAXIS has chosen or understand that there are these stress points that we need to use. If that's the thing that I am the thing that I'm showing here as a command, this is critical for you to know. So add curve points, and then you put the node, and you put the x coordinates and the y coordinates. So you copy this in here in the command line like that, for example. It will generate what you've got. Or I'm repeating myself just for confirmation. If you go to expert run commands, you put it here and you run. But the command line takes only one by one. We are not interested in changing anything here. So basically, I am happy with what I got so far. But these two commands, the way they are, the syntax, these are critical. I put them several times here for you to see it. So by now, I showed you how I created the stress points to be queried. Another way actually is to use Python itself to generate these stress points for you. I'm not doing this here just to show you a different approach of doing things. So if we go to the stage construction, I have already analyzed the model. So the first one is generated the geostatic stresses, nothing fancy here. In the next one, I basically just backfilled here to apply the retaining the earth pressure. For phase 2, this is seismic. We will cover it under the dynamic in the next question or in the next example. So I'm interested in this phase 1 here. So if I output the results here, it will show you what we've got, and then we will go to the script. So this is basically what we have here, and if you double click on this interface and you go interface stresses, if you are interested in the effective sigma dash n, so it will give you, this is basically the distribution of the earth pressure. Okay, if you are doing this for your own project, it's a good idea that you take it out and then also you draw on it sigma active, and you draw on it the at rest pressure from using just K naught, and then you should see this actually going somewhere perhaps in between, or the minimum pressure would be the active. Anyway, so all I'm saying now is I have a model that's currently working, and we need to query this earth pressure automatically. This would help when, imagine if you have several dozens of instances of this retaining wall where the height actually keeps changing because of sloping the ground or because of whatever, and you need to automate this process so that you don't have to go every time and see the calculation results and then double click on it and see the value and then go to PLAXIS table. It's quite it's a quite slow and daunting task. So, for example, if I go to mesh connectivity plot, you see here, so this is what you've got here. So if you want to draw a line to get the earth pressure, so you can come here and say, okay, I need to draw the earth pressure on that line. I'm just giving you an example, and I go to stresses, and Cartesian effective stress, I'm after sigma dash xx. So this is what you will be getting, and then you go to table, and then you get xy and sigma dash xx. Quite involved process. And then you take this to Excel, and then you draw it there in Excel, process it further. Okay, so this is a manual process that will consume some time, and also it's quite boring process. So now, if we are interested in using the Python script, like I showed you, we'll go to Expert Python, go to Editor, and say Start. You need to take note of this password. Port is 1000. Start server. Okay, close, and then it should open for you a blank. So this is what you will. I don't think I made a mistake. So this will be something blank like that. Now all you need to do is to go to the project folder, and I gave you this Python script, earth pressure static rect wall.py. You have to have the extension .py. So double click, and now I got the script that you get in this course. And here is a bit of explanation of what this script does. Okay, so this in Python, when you see this marked, it means that this is a comment. This is not a command line to be executed. So it says script to extract the stress point results from PLAXIS output. So it tells you that this script connects to the PLAXIS output server, retrieves stress points, and extracts horizontal stress sigma xxe here, which is this how PLAXIS understand. If you are interested in sigma xx, horizontal stress, so it's a sig. This is a syntax. Sig xxe is for effective. If you are interested in the vertical, so you go sigma sig yyE. If you are working on a 3D model and you are interested in the Z, so all you need to change is this one, say sigma zz, and E, like I said, for effective. And it gives you some instructions here. Ensure the PLAXIS output server is running, and then if you need to adjust the connection details. So connection details. So this is a password, if you remember. So you need to. I'll come back to this. You need to paste your password that you saw from the server. That's important. And now, based on this, it says ensure the PLAXIS output. Unfortunately, this is not very friendly here, but okay, ensure the PLAXIS output server is running. So this means that I have to go to this, and they say go to output. It has to be open based on the instructions that you have in the Python script. I'll continue with you here. So all these are, like we said, these are just comments for you or instructions to follow. And then the code starts from here. I'm not going to explain lots of things, but for example, this how it calls upon this library of the PLAXIS scripting, which I explained before. And this, the one underneath it is for pandas. You see you have the pandas here. And then it also get the datetime library, because we need to see actually the execution time of this. We need to know whether it takes 1 minute, 2 minutes, 3 minutes, 5 minutes to run this. Host, you don't need to change this at all. Output port is 1001, so you need to know that whether this is correct. If I go here and they say options, expert, say configure remote scripting server, so this is 1001. Again, if you put 10,000, we know it's booked, like I said before. So this is 10,001. So close. So we need to make sure that this is 1001 for the output port. I'm interested here in the output, so there is no point in going to the input. And then this continues here. I need to show you something interesting here. For the phases, remember, for the phases, basically, this is how Python access one item in a list. So you see between these two square brackets here. So you can have, you say, this is phases. If you have 3 phases, like the one we have here phase 0, phase 1, phase 2. So this actually also follows suit. So you can, if I say, just for the sake of the explanation, so if I go back to this, I will copy it so that I can explain it here. So this basically, it tells PLAXIS that I am identifying something here called the phase, and this phase is, you go to the output, and the phases, so this is one of the how to access the phases in PLAXIS, and say -1. I could have say 0, and I can say 1, and I can say 2. So basically, or I can say 0 only, so it would go to phase 0, or I can say go to phase 1, so it will interrogate the results from phase 1. I have here phase 1. If I go to phase 2, then I get to phase 2. Now, if I say -1 here, basically what it says is go to the last item. This is how the Python basically manipulate the items in the list. If -1. So in this case, -1, it means they're going to go to phase 2. And if I say -2, it will take the second from the last. So the second from the last here is phase 1, which is the one we are interested in, because I said to you, forget about this for now. This is dynamic. So the phase I'm interested in is phase 1. So this means that I need to go here and say here, I explained these phases. Yes, correct. So this would be -2. Okay. And you may wish to specify the step. In this case, I am interested in the last step of the analysis. Why? Because if you go to the PLAXIS thing here, double click on here, and I'll bring this to this screen. So basically, maximum number of steps stored here is 1, which is the last step in the analysis. You could have stored 3 or 4 or 5 depending on your analysis. This would be useful when you do dynamic analysis, as I will show you later. So, but here we are interested in the last step. PLAXIS by default gives you this this thing here. So I close this one and I go back to my script, and I know this -1 means that it's telling PLAXIS I am interested in the last step, which is for static analysis. It will always be the last step. Always be the last step. So what else we are having here? This is just something that it's telling you that it is using sigma XXE. If we are interested in something else, you will see here as we come down. So more of the codes. Well, for you, your input has ended here. All you need to do is basically confirm this here as a password. And if you are interested in it changing the stress you are interested in, you can see it later here. So this is just, this will be printed on the console. If you are interested in something else, you can say sigma YY, you change this, but this is not into action. It's just a message for you. If we go down, so this is how PLAXIS basically identify or query the results. Because we are interested in the x-coordinate of each point, so the x-coordinate is extracted, y-coordinate is extracted. Sigma XXE value, so these are just parameters. You can name it anything, you can give it your name, it's not an issue. But what you need to comply with is how this is done. So this is how PLAXIS will answer to this. So it says, go to the output here, O for the output from the global module here. So output and get curve results. This has to be used. What is curve results? Curve results are all the points. Let's check this one here. Are all these points that we have specified. These are called curve results. And if you remember, we have here this thing here. So these add curve points. So these are the points that we have specified. Okay, and remember we have a code here that can do this for you, and all you need to do is basically just if you copy, if you don't have it, so X, you go to your code. So this is a code. You go insert module, and then whatever module you have, you paste it, and here you go. So I'm actually not interested in changing anything here. And then you go to this, and then assign macro, and you assign it to the one that you are interested in, which is generate PLAXIS syntax with custom output. Okay, we explained already how to process this. So let us continue with this. So we have the get curve results, and this syntax is basically what PLAXIS need to understand. So I am telling PLAXIS to go to the stress point, and then get the last step, and we have the last step here defined. This is a stress point, as you can see, which is basically going to be a list, and then from the global output, and then the result types, it has to be this way. And the dot soil, I'm interested in the soil. I'm not interested in something else, not like a plate or like an embedded beam, or I'm interested in stressing the soil, and then get X, which is the coordinate here. Same for Y, same for sig XXE. That this is what I'm interested in. If I'm interested in the Y, so I would come here and say YY, something like that. And then you change this also to YY, just so for consistency of the message. But I'm not interested in changing anything here, so I am undoing what I did here. Here, we basically, this gonna print everything to a file, okay? But the file, the way we are doing the file name here is quite clever. In case if you have this file for some reason open and you run the script, so you would get an error. So basically, every time you run the script, the file name will change according to a time step element we have here, timestamp element that we have here. So by now, I have explained everything here. So all I need to do is to run this. So to run this, you can go to Tools, Go, or you press F5. Okay. Remember, you need to have everything open here. You may get errors sometimes, and then you query these errors. But hopefully this. I press the F5 now, so it's running. Hopefully it will. It says connected to PLAXIS Output server successfully. And then it is retrieving. I have a total of 24 stress points. So these are all messages, and actually it gets your results in the console. But I have also here, this is a file name. This is a file name in PLAXIS. Okay. So if I go now to, hopefully you'll have this. Okay, so if I look at this here, I see, let's say date modified. So I see a file here. So this is a file. If you can see, this is a file name. Okay, that was just generated. If I double click on this, I should be able to see the results. So you have just double. This is a CSV file. So this is a CSV file. So it has. Okay, I don't know why I'm having this. Okay, so this is a result, which is basically similar to what you have in the console here, but in a structured manner. So it says point ID, that's fine. X coordinate, the X coordinate is almost constant, okay, because the stress points may deviate a bit from the exact number. It depends on how it is distributed within the elements of PLAXIS. This is X coordinates covering from 5 to -2, as you can see here. Again, this is not going to be 5 exact, and this is a sigma XX I'm interested in. So if I would like to draw, so I can basically choose these two, and you must have something here. So this would be basically the distribution. I think I need to swap those. So I'm plotting sigma XX versus Y, and I can basically perhaps put a line here. So this would be, well, those stuff here a bit funny. So if we go to let's just retain the no line here. So this is the distribution. It's doing like that. We have a point here which could be an outlier, but basically this is the distribution. Let's check some of these values against the PLAXIS to ensure that we are getting the right thing here. Okay, so if we go to PLAXIS and we need to get the values at certain stress points, what we can do, there are lots of ways to do this. So assume that we're going to draw a curve. So new, and I will draw a curve, and in this curve I'm interested in the stress points. Well, here it's not going to give you, that's quite interesting that we talk about this, because I don't have nodal points here. So you don't have the X coordinate of the stress point. Let's just give you the deformation. But let us see. This is supposed to be like the stress. So we go to stress, Cartesian effective stress, and it will be sigma dash XX. And here for the same point, you are supposed to have the Y coordinate here. So it's not coming here. So because we don't have nodal points, or we don't have actually the coordinates here. So querying it by the stress point curve is not a good idea. So we go to this, and all we can do is we draw the line here, and in this line we need this X to be 11. So we're getting very close. So this is 11, and we are getting, say, I'm not sure this needs, it did not come happily, so we'll come back to this. So draw the line. Well, there are many ways to skin a cow, so let us, okay, so we go back to stresses, cross-section or Cartesian. So we're interested in the sigma dash XX, and let's choose a point to do the comparison so that we can confirm. This is not the one. We need to see what we got here. So let us say we need a point at, say, at elevation 2.36. So what you can do, you can come here and keep moving here, and then see down here. You see this is the coordinate. So this is one way to check it. So we are interested at 2.36 elevation for the Y. 2.36, so we go down. Watch this space here. 2.36. So I'm somewhere here, okay. And you see I have here about 11.22 kPa. So let us see what we've got here. It's 11.2, so it's correct. Okay, so this is one way to do it. Another way to do it is also to come here and choose, come close to this. Watch out this space here. So 11, we need to 2.36, so we keep going up. 2.36, 2.36, and you watch the last row, so 2.36, something like that, and then 2.36, 2.36, and we are getting there now, 11 point something here, okay? So we even have the room to go a bit up. So it's 11 point something. So this means that our script is reading the earth pressure correctly, and we can take this data and manipulate it and do whatever we are interested in. See, the maximum pressure here is 41, and that's it. So in a nutshell, now you know now how to use this. You know what to change here. You need to know what stress you are considering, and you can change this at will. And well, it's a fantastic Python script, and it's quite handy. You can use it for anything, basically, where you have points that you want to extract the pressure from. So with this, I conclude this session, and I'll see you in the next more interesting one with the same problem but under dynamic analysis. So I'll see you there.